Okay, right. Good. Well, I think we'll make a start. So, welcome everyone. I'm here to sort of host the session for this evening, but I'm just going to briefly hand over to our chair, Les Jones, who I think will say a few words to welcome everyone. Over to you, Les.
Right. Okay. First and foremost, can anybody hear me? Yeah.
Yeah.
I don't know what your situation is like, but I'm getting stuck in video and audio at the moment. So some people are sending a Norman Collie at the moment, but hopefully you can all hear me. I'll carry on. Right. So first of all, I'd like to welcome you all again to another online meeting of the Havering Astronomical Society, the first one of 2021. I'm hoping that you've all had a good new year and are managing to keep safe and well in this current lockdown number 3. But as towards most of last year, we are managing to continue producing these meetings, and hopefully you're all going to find them as interesting as we have done over the last few months. It looks like from the current situation that we're going to be continuing holding our meetings in this format, and also it looks like that we're gathering membership and new members and new people coming along as we speak. And I believe this gentleman, Clive, is it? Clive's joined us this evening. Welcome, Clive.
Thank you.
Hope you enjoy it tonight. And as I say, there'll be many more of these during the evening. So say welcome along, and I'll pass back to Les, who's going to introduce our speaker this evening, Professor Marc Schumann. Thank you, Les.
Perfect. Great. Thanks, Les. And Mark, just to avoid confusion, I'm Les B and that was Les J. So, okay. What can I say? We often have speakers who talk to us about tangible things, things that we can actually see and touch and get a good sense of. But Professor Marc Schumann is here this evening, has kindly agreed to talk to us about things that we can't quite see yet, but hopefully we will be finding the evidence for in the very near future. So just by way of introduction, Marc is the professor of experimental astroparticle physics at the Physics Institute at the University of Freiburg. I think that's in the Black Forest, isn't it, region of Germany?
Yes.
And Marc's research focuses very much on the search for the elusive dark matter, in particular with a gas called Xenon. And I believe the actual program, the research program that you're leading is actually called or has Xenon in its title as well. So Marc's role is very much about designing and building and using those dark matter detectors, and I'm sure he'll be telling us a lot more about that, but also about, in particular, how to improve that, and hopefully what dark matter will actually tell us about the universe as a whole. I'm not going to say anything more, Marc. I'm going to hand over to you now, and if you want to tell us a little bit more about your background and how you got to here, that'll be great. But otherwise, the floor is yours.
Thank you, Les. Thanks for the kind introduction. Thank you to everybody for joining and for the interest in our work. Somebody from you, I don't remember, contacted the speaker's office of the Xenon dark matter experiment. That is the big enterprise I'm a part of. So I'm not actually leading it. We're just providing important contributions to that, asking for a speaker to present some of our new results, and obviously I will try to give you a talk that you can grasp. Basically, I'm not going to give you a real scientific expert talk, knowing from talking to Les that you have very different backgrounds, from professional astronomers to layman amateur astronomers. So I'm really giving that talk for you, so please feel free to ask questions also during the talk. Usually we have questions at the end, but if you think that something is completely not understandable, that you're missing a key concept or something like that, please feel free to interrupt via less to ask, because obviously it makes no sense if we sit here together and you have no clue what I'm talking about. Especially in that stupid Corona situation. Usually when we are together in a lecture hall or somewhere, I can see your faces. Now I can only see my presentation and probably a small picture of me, so I cannot see your faces and I cannot see when you're falling asleep. And since you're muted, I can also not hear when you're falling asleep. So please, I have absolutely no problems to answer questions at any time. And if it's getting too long at the end, we will skip some parts. So no worry about the time. Okay, so let me share my screen. Does that work already? Yes. Oh, wow. Okay, does it work? I cannot hear any.
Yep, I
Okay,
can
good.
see your screen, and there is just on the side a little grey box. So if you could perhaps just close that.
Oh, it will not. It will not. That's me and you and things like that. But it will not go into any content.
Okay, perfect.
Okay. Yeah, the title of my talk is Exploring the Dark Universe with Xenon, and you see that Xenon is written in capital because that is the name of our experiment. So this is the world you know. At least this is what Google tells me what the Havering Town Hall looks like. The key message I want to tell you is that the world with an astronomer or physicist's eye looks something like that. I did quite an effort to have only 5%, surprisingly, with an airplane in it, light, and everything else is dark, because this is at the end our current view of the universe. About 5% of the universe is normal matter. About 25% of the universe consists of something that we call dark matter, and about 3/4 of the universe is dark energy. And you see the difference here. Dark energy, I just leave black, while dark matter, I still make the picture. Dark energy, strictly speaking, we have absolutely no clue what it is, and we will not cover it in that talk anymore. We have quite some ideas what dark matter could be, and we think there is also a chance to detect it. And this will be the topic of that talk, how you detect dark matter. So we'll start with, why do we know that dark matter is there? How can you detect dark matter, and what else can you do with these very, very special detectors? So just to give you a feeling about, there's a zero missing, about 100,000 dark matter particles pass through your thumbnail per second. So there's quite some dark matter out there, and also in the room that you're currently sitting in. So there is a chance to detect these particles. So let's start with the first talk, evidence for dark matter. So how do we know that dark matter should be there in the universe 6 times more than ordinary matter? And you probably know some of these already. One of the most famous one, even though not the first one that was put forward, is the rotation curves of galaxies. You have seen these pretty images of spiral galaxies or barred spiral galaxies before. And if you just look at them, you see that there's a lot of mass in the center, that's called the bulge, and then there's somehow less stuff in this galactic disk. And we know that these systems rotate, and well, there's quite some similarity to the solar system, where you have the big mass of the sun in the center and the planets all around. So if you now think about what is the motion, the velocity of that stars around the galactic center, what you expect from just looking at the picture is the ordinary Kepler rotation as in the solar system. So that if you take the square root here, the velocity, the radial velocity with the distance from the galactic center decreases with 1 over the square root of the radius. This is what you expect. What you observe looks like that. the outer parts move much faster than they should. So instead of an rotation curve, so that's again distance, velocity versus distance, falling with 1 over r, the square root of the radius, it keeps constant. If you now go to real measurements, not animations, here this is M33, even in regions where you cannot see any stars anymore, you use hydrogen 1 lines to do these radial measurements, radial velocity measurements. You see that it's not decreasing at all. If it all is rising, it's flat, far beyond visible stars. And we can explain such a behavior, but not with this standard classical bulge and disk picture that we see. But if you embed this entire galaxy in a much, much larger, we call it halo, consider it a ball, made from something else, something that only interacts gravitationally, because obviously we cannot see it, and it has a density profile of 1 over r squared. So it is not a constant ball, ball with a constant density. The density decreases with 1 over r squared. Then you can explain this flat behavior. And as we cannot see the thing, we call it dark matter. Another indication comes from the largest scale that we have in the universe, and this is the universe itself. So it comes from cosmology. I'm pretty sure that you've seen this nice picture before. So this is our current understanding of the evolution of the universe. Everything started with a Big Bang, and then there was this short period of rapid inflation of space. And what we can see now, basically, we're here now, and if you look back in time using our telescopes, the oldest thing that we can see with electromagnetic radiation is this afterglow from the Big Bang that was created about 360,000 years after the Big Bang. It's the so-called cosmic microwave background. So these photons that come from there, they were extremely hot during the Big Bang, but now they cooled due to the expansion of the universe to microwave temperatures, 2.7 Kelvin to be precise. And if you look in detail at this map of the earliest universe that we can see, it would look utmost boring. What I'm showing you here is temperature fluctuations at the 10 to the minus 5 level, so 0.00001. Because this is really 2.7 Kelvin everywhere. But if you now look at tiny temperature fluctuations at 10 to minus 5 level, you see that some spots are hotter than the blue ones, and some spots are a little bit colder. And what we think is that this is basically the inference from the primordial fluctuations in this quantum fluid that created the universe. And this gives a lot of information about the ingredients of the universe when we analyze that. So what we can do is we can basically, physicists call it a correlation analysis, but what is it? The question is, what is the typical size, the angular patch size? The whole picture here is 360 degrees. And so what is the typical patch size of this hot and cold spot? And what you can see is that the typical patch size is 1 degree. That is the reason for that peak here. And now you can analyze that data. This is the angular scale. So at different scales, you have different strength of fluctuations, and you can model that. And this model looks rather complicated, but at the end, it is only 6 parameters, and one of them is the amount of dark matter in the universe. And what you can see is you have less dark matter, more dark matter. Different lines produce different curves, but there's only one that fits the data very well. And the experts can tell from the fact that the second and the third peak here have almost the same height, that there's lots of dark matter in the universe. And in fact, this observation of this cosmic microwave background made cosmology a precision science. So from that, we can really nail down these ingredients of the universe to a sub% precision by now. There's another thing why dark matter is very important for us. Dark matter is 6 times more abundant than ordinary matter, even though we have no clue what it is. And being 6 times more abundant than ordinary matter, of course, it has a lot of impact on the evolution of structure in the universe. Basically, if you now simulate how the universe evolved, starting from a very, very high redshift. This is 40 million years after the Big Bang, starting with some inhomogeneities given by the cosmic microwave background, because this is the primordial fluctuation that got amplified by inflation. And then you run that simulation. What you see is that you get this structure of filaments and voids in between something. Basically, every dot you see here corresponds to a galaxy. So this is of course not the entire universe, but a rather large part of the universe. And if you now compare these simulations that were done, assuming that there is a sizable fraction of dark matter in the universe, and you compare it to observation, this is the Sloan Digital Sky Survey map of galaxies in the universe, you see that you essentially get the same structure. Of course, the real analysis is not done by eye. Sophisticated computer code who do these kind of comparisons. But what you see is here you have filaments and voids in between. Here you have filaments and voids in between. And also from that, you can deduce dark matter is a very important part for our universe. So at the end, what is this dark matter that we are searching for? We look for some matter with the following properties. It must be invisible. Invisible in the sense it must not interact electromagnetically like light or charged things or magnets, not via the strong interaction that binds nuclei together, because otherwise we have seen it already. These interaction strengths are so strong. Maybe very, very weak via the weak interaction that governs radioactive decay, maybe a new fifth force, maybe only gravity. It must be cold. So we talk about cold dark matter, where cold just means slow. So the particles are moving with non-relativistic velocities. It must be almost collisionless. That means it does not collide with itself, does not collide with other particles, which is kind of a consequence from this invisible. So if something does not interact, there are no collisions. And it must be stable. Stable means we know of many particles that have some of these properties, but they decay. Most of them in rather short timescales. Here we need something that is stable over cosmological timescales. If we now look at the menu from particle physics, and I'm sure that this is a rather complicated plot, we don't have to go into any detail. So basically, this is all the known elementary particles we know of. The visible universe, everything that is relevant for us, is just made out of these particles, an up, down, and down quark and an electron. Everything else we know about, it is usually short-lived, apart from the neutrinos down here. But this is the physics we really know very well about. There have been plenty of Nobel Prizes for that. The last one here was the discovery of the Higgs boson that was predicted 40 years ago. So we know these particles very, very well. The problem is none of these particles has the properties that we're looking for. Not even the neutrinos. The neutrinos are almost invisible. They're almost collisionless. They're stable, but they're not cold. They're very light and they move with relativistic velocities, basically at the speed of light. So they cannot be the dark matter we're looking for. So we need something new. And one of the things that was invented, a new particle is basically the so-called WIMP, weakly interactive massive particle. That's basically just that particle that fulfills everything from that shopping list. It's weakly interacting, massive, and it's a particle. And what I will tell you about is how do you search for these steps. Of course, this WIMP is really just one of many candidates, but many of us consider as the most well-motivated one. If you look here at the plot that spans 50 orders of magnitude in interaction strength, forget the unit, does not matter, and also the mass of this dark matter particle, both of them are totally unknown. But of course, not everything in this parameter space, interaction strength versus mass, is theoretically allowed. So you see these typical models somewhere in this parameter space. And the WIMPs here, they're predicted by many theories, theoretical models that basically predict something beyond the standard model of physics that we know. They predict these WIMPs. Something else that I will shortly mention later in the talk is the axion. For the moment, this is just another candidate, solves other problems, could be dark matter. The difference here is it's much, much lighter than the WIMP. The WIMP is something like 100 GeV or so. I see the question here, but it just popped up. Can somebody repeat it?
Yeah, hi, Mark. You mentioned right at the start, actually, about 100,000
Yeah.
particles flying through 1 square centimeter. How do you know that if we haven't yet found them?
I will answer that question in a minute because I have the right picture to explain it properly. I will come back to it in a minute.
Perfect.
I think it's in 2 slides or so. So I don't think that was totally convincing that dark matter exists for you, especially if you never heard something about that. But what I can tell you is basically that's the essence of the previous slide. There's plenty of indirect evidence that exists. I've shown you 1, 2 here, but there are many, many more that I skipped for time reasons. So 99.5% of physicists are sure that dark matter exists. It does not mean that we're able to detect it, but we can only explain these things with dark matter. So now the question is, how do you search for dark matter? You need a detector to search for anything, telescopes, cameras. This is a very complicated detector. That's the CMS detector at the Large Hadron Collider in Geneva. They also search for dark matter, but that's not the kind of search that I'm talking about. A simple detector is the camera of your cell phone. It's also a particle detector. It detects light particles. Light particles are photons, and if they impinge on, for example, a pint of beer, there's a scattering process here, and it scatters light from the beer into the lens. Then it creates electrons here, so it creates electric charge. They're amplified, and then they're read out. This is a particle detector, and every one of you carries it around. We also use something like that, a little bit more sophisticated for our purpose, but the principle is always the same. So how do you search for dark matter? It's really as simple as pool billiard. What you do is you place target atoms. So basically all these billiard balls here, this is our detector. We place not one, but many of these atoms in the laboratory, and the laboratory is on Earth. And the Earth is in the solar system, somewhere here in the outskirts of the solar system, of the galaxy, of the Milky Way. So now coming back to the question, how much dark matter is here? How do we know that? The canonical value is 0.3 GeV per cubic centimeter. It's a third of a proton mass per cubic centimeter. So how do we know that? Well, we can measure that. We can measure it in 2 ways. One is we can measure our own galactic rotation curve and measure the rotation velocity here. We cannot measure it really here, but we can measure it somewhere else and then assume that's the same everywhere. And from that, we get the rotation curve of our Milky Way, and then we can calculate back how much dark matter is here. The other thing is what we can do is we can look at nearby stars and how they move in and out of the galactic plane. And from that motion, we can deduce the dynamics of that process, and we can reconstruct the amount of matter in our local neighborhood that we don't see. From that, we get that number. So that is the first part of the 100,000 particles per second per square centimeter question. The next thing is now we need to know how fast do we move through this dark matter halo, through this 1/3 of proton per cubic centimeter. And this is the rotation velocity of our sun. This is 230 kilometers per second. It moves around the galactic center. And if you take that number, if you take the local density and assume a dark matter mass, this you have to assume. We don't know what the dark matter mass is, but there are certain well-motivated models that tell us that the dark matter mass is around 100 GeV. This is 100 proton masses. Then you get to the 100,000. If the dark matter is 10 times lighter, you get to 1 million. If the dark matter is 10 times heavier, you only get 10,000. But it basically gives you the right order of magnitude. Does this answer the question?
Great, thanks, Mark.
You're welcome. So, but back to the problem that we have here. What we are doing is we place many target atoms in our lab, and these are all part of our detector. And there's a lot of WIMP dark matter particles flying by. The typical velocity is 230 kilometers per second, because that's the rotation of our sun through this galactic dark matter halo, which is not co-rotating. So basically, you really have to assume that the galactic plane is rotating, the dark matter halo, simplified picture to first order, stands still. It does not follow the rotation of the galactic disk. Because dark matter does not interact, it has no way to lose angular momentum. So if occasionally one of these dark matter particles hits one of these nuclei, what will happen is it kicks it, like in pool, and creates a signal that we can detect. So what we see in our detectors is not the dark matter particle itself, but it is that suddenly one of our target atoms gets a kick and starts to move. That's the signal that we see. One important point to understand our detectors and the searches we do and the complications we have is that you have to understand that there's lots of radioactivity everywhere. I will come back to that later in a second. And this radioactivity is usually related to gamma and beta decays. And gamma particles are just photons, beta particles are electrons or positrons. They are electromagnetically interacting particles. So they will never interact, not never, they will not really interact with the nucleus, they interact with the electronic cloud. This is chemistry at the end. So they produce electronic recourse. And if your detector has the means to distinguish between signals that were produced by a moving nucleus or moving electron, you get rid of a large fraction of our background, which is the main job that we have. If you want to find the needle in a haystack, you have to get rid of everything that is not the needle. The signal that we expect here is at the end very easily distributed, very boring. So this is basically just how often does something happen, and this is the energy of that recoil here, and you see it's a featureless phonic spectrum. So you don't get a line or something like that. Maybe some of you saw images of a Higgs discovery, then at a certain mass, the Higgs mass, you see a peak popping up. This is not what we expect from dark matter. And just a very, very quick thing here, this electron volt or giga electron volt I'm always using here is really just a unit of energy. An electron volt is the potential energy, or sorry, the kinetic energy that a resting electron gains if it moves in an electric field created by 1 volt. And 1,000 electron volt is 1 kilo electron volt, 1 million, 1 mega electron volt, 1 billion is 1 giga electron volt. And you all know this formula, Einstein E equals mass times c square. That means you can always express a mass in terms of energy divided by E squared. And this is what we usually do, because then the proton mass is something like 1 GeV. We always don't talk about the 1 over c squared because everybody knows that. So we say the proton mass is 1 GeV and not 1.67 times 10 to the minus 27 kilograms, because this unit is just not handy. But whenever you see something like here, keV, that tells you just, okay, this is kilo electron, 1,000 electron volts, and 1 electron volt is again, you can express it in joule, but I do not even know. You can do the back conversions, a very, very small amount of energy. In most cases, for the talk, it does not matter. There was a question again. Can somebody repeat it, please? I don't see it.
Yeah, it's from Les J. You said earlier that dark matter was collisionless. Is the interaction between the WIMP and the nucleus not classed as a collision?
No, it is. So the point is, it's an extremely good question. We don't know that this collision can happen. At the moment, we just have observational indications, evidence that dark matter interacts via gravity. Gravity is the weakest force that we know, and an interaction, so really this pool table interaction would never be stable via gravity. So our experiment, and every experiment aiming for detection of dark matter, would be to fail if dark matter is really, 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 really collisionless. On the other hand, we need to produce dark matter somewhere in the early universe after the Big Bang. We need to produce 6 times more dark matter than ordinary matter. And we understand very well how all other matter in the universe was produced. And if we assume the same principle of producing dark matter in the early universe that works extremely well for everything else we know, then there must be a very feeble interaction between dark matter and ordinary matter. But it's a very fair point. At the moment, it's an assumption. We don't know whether this interaction exists. But at the end, this is what we want to measure. Our experiments aim at measuring the interaction strength for these collisions. Okay. Again, this is exactly shown in that kind of formula here. So the event rate that we aim to measure is proportional to 3 ingredients. One of them is the size of the detector, here dubbed with n. If you double the amount of target atoms in your detector, the chance for, if you have a given interaction strength, to see something gets doubled. It's directly proportional to the local dark matter density. If in the lab where I place my detector is no dark matter, because we live in a gigantic dark matter void, obviously we'll never be able to see something. We think that this is a third of a proton. So that should be fine. And this is what we want to measure at the end. This we know, this we think we know. Given the rate that we measure, we can then deduce what is the interaction probability for this process here. What we know is that the rate is extremely small because we haven't seen anything yet. That means much less than 1 event per kilogram of detector material in year. Now think about your CCD in your cell phone. It's maybe a gram or so. Our detector have the scale of many tons by now. We operate them for years and we see nothing. So that means these rates are really, really small. So what we're doing is we're really searching for rare events. And if you search for something very, very rare, you need very low backgrounds. That means you will never place your detector, and this is a sketch how such a dark matter detector actually looks like. That's a detector here inside a large shield in front of your town hall, because if you turn on your magic eyes, then you will see that the sky is not blue, but there's lots of particles. You know that the outer atmosphere is bombarded with cosmic rays. These cosmic rays produce secondaries, they produce showers in the atmosphere, all that you just cannot see, but it's there. And of course, it would penetrate directly into any shield and to our detector and would swamp every signal. So what you do is you go deep underground. Where we place our detectors is below that beautiful mountains of almost 3,000 meters height in central Italy. And this is the Gran Sasso mountain. It is inside the longest two-tube tunnel in Europe. There's a gigantic laboratory, the Laboratorio Nazionale del Gran Sasso. And there, in one of the 3 big halls, we place a large water shield. Come back to that in a second. You see here the construction of that thing. Our water shield has a diameter of about 10 meters and 10-meter height. So you go underground to mainly get rid of muons. Muons are basically the heavier siblings of the electron. And we get, after 1.5 kilometers of rock, we get 1 million times less muons than we get on the surface. These muons are not a problem in general at all. The problem are muon-induced neutrons. So muons can interact, they produce neutrons. You know, the nucleus it consists of protons and neutrons. The thing about the neutrons is that neutrons are neutral. So they also don't interact with the electronic cloud of the atom, but with the nucleus, as our dark matter candidate. So basically, neutrons are very, very bad backgrounds for us. That's why we have to go underground. Of course, there are many, many other background sources. There are neutrons from nuclear reactions. There's natural radioactivity in the detector itself and also in the detector target itself. A very small detour. So what is radioactivity? I guess most of you know alpha decays, beta decays. they are basically transitions of nuclei into a lighter one by the emission of another particle. And there's gamma radiation that is at the end the de-excitation of an excited nucleus. So you have a nucleus that in an excited state, it decays into its ground state or lower excited state under the emission of a gamma ray. And these particles, of course, they are everywhere. This is the natural exposure, or even also including artificial radioactive dose that a typical human in Europe gets. And you see that about 25% is artificial, that's medical exposure, X-rays, PET scans, and so on. But there's a gigantic amount that is just natural radioactivity. So radioactivity is nothing bad at all. It is really everywhere. Every body of you, a typical human, has an activity of about 8,000 becquerel. So 8,000 decays per second happening inside your body. About 4,000 of these particles come out. So you emit 4,000 gamma rays per second. The other 4,000 is a beta particle that stays inside your body. That just contributes to here this terrestrial radiation that your body gets. That's just the potassium-40 inside your bones. You probably heard of radon. Radon is a radioactive gas, part of the uranium chain produced in supernovae. It's emanated from every surface. You might have a higher level in your basement. All that stuff is around us and produces signals in our detectors. So what we have to do, and this is why we have these gigantic shields, is we have to get rid of these backgrounds. One thing that we do is we select our detector construction materials. So an important ingredient for our detectors, to build our detectors, is just stainless steel. We just don't go to the local hardware shops and just buy some screws, because you never know whether the screw had a history in a Russian atomic submarine. So what we do, every screw, every component, everything we place in our detectors is screened in so-called low background screening facilities. This is one example that my group operates, but also in the UK, in Bolby, that is near Saltburn by the sea, there's a smaller underground lab, and there's a big screening facility. Each of these facilities is basically there to select radio pure materials. You put that in there, you measure for 3-4 weeks, you get the radioactive fingerprint of each component, and then you say, yes, this material is good or it's bad. And at the end, for big detectors that we are now operating, at the end, so we are underground, we are inside a rather large shield. The only radioactivity that we care about is really the detector itself. You need to contain something, you need to read out something, you have cables. The dark matter target itself, in our case, it's xenon. There are some isotopes in xenon that are radioactive. You have to deal with them, and at the end, it is neutrinos from the sun. I will come back to that. Depending on the energy, they interact with the electrons or they interact with the nuclei. And this is, of course, a background you cannot shield. There's a gigantic solar neutrino flux, and neutrinos just penetrate through 1.5 kilometers of rock. They do exactly the same as the WIMPs, dark matter particles. They also don't care that we are 1.5 kilometers below granite. They just pass through. Okay, now let's come to the next part. That's the xenon experiment. This you can see here. So therefore, we are a, let's say, medium-sized collaboration, 170 scientists, 28 institutions from all around the world. And we built particle detectors to detect dark matter and other rare processes with an increasing sensitivity. We started years ago with a small detector at a 10 kilogram scale, 100 kilogram scale. Now we are at the ton scale. This detector, I will show you some results from that, is already dismantled, and we are now in the transition to a detector with a almost 6-ton target mass. And at the end, I will very briefly talk about that one. So basically, you see is a double logarithmic plot. That is our sensitivity. The smaller the number, the smaller the interaction probabilities you can probe. And to be able to reach down here, you have to increase your detector volume. You need a bigger N, more atoms to scatter with. Our detector is a so-called dual-phase liquid xenon time protection chamber, and it sounds complicated as a rather easy thing. Remember, what we do is playing pool. Our detector is at the end a bucket, so this is a cylinder filled with xenon. Xenon, something that you might know from your cars, is a noble gas, but if you cool it down to 100 degrees Celsius, minus 100 degrees Celsius, it gets liquefied, and you saw here, it looks like water. At the end, it is 3 times more dense than water, it's a density of 3. Also, if I cannot repeat it easily, it has some different dielectric properties and so on. But since it's only minus 100 degrees Celsius, it's rather handy to work with. The interesting thing about xenon is it's a very good scintillator. What is a scintillator? If a particle hits the xenon atoms, it starts to emit light. And this is what we want to see. We want to see the consequence of the pool billiard process. So we put photosensors above and below our dark matter target into the cylinder filled with liquid xenon. And if you look here at the detector signal versus time, if something interacts here, it creates light. The light scatters around the detector and is seen by these photosensors, and it creates a tiny light flash, which we see. But it does not only create light, it also ionizes the xenon. So it liberates the electrons from the atoms. We put an electric field across this liquid xenon volume, and charges move in an electric field, so these electrons move upwards here. But this does not create any signal. So if you look at the time axis here, time just passes by, but the detector sees nothing. At this time, the electrons move upwards. Now we put here a second electric field that extracts these electrons from the liquid into the gas phase, where they scatter with other xenon atoms and produce a second light flash, which is amplified by this extraction process here and is directly proportional to the charge. So this is what we expect to see from an interaction. We see a small light signal, then a period of time nothing, and a charge signal. The nice thing with this detector is you can reconstruct the interaction position of this event in your detector in 3 dimensions. The z coordinate you just get from the time difference between the two, because you know the electric field strength, and the xy you get from the hit pattern of the photosensors. So we have many photosensors up here. This is what you see here, and since it's a very localized signal, you know that the interaction was here. The other handy thing of this detector is that it can distinguish between your signal and background. If you look for an electronic recoil, so this is really something scattered of the electron, you get for the same light signal, the light signal is the same, a rather large charge signal. If you look at the nuclear recoil, so basically something like dark matter interacting with nucleus, you get a rather small charge signal. So if you plot the ratio of the two versus the energy, you see a separation of populations. So the background lives up here, the signal lives down here. So that means if you know that the signal you're looking for, dark matter, cannot interact with the electrons, but it must interact with the nucleus, you search down here, away from the background that you have. So this is one of the key components here. This possibility for 3-dimensional vertex reconstruction is the other one. We know that backgrounds happen at the borders of our detector. We have a rather large detector, so you only take the inner part for the search. So this is how our detector looks in Italy. This is the water shield. This is just a banner attached to the shield that people have the feeling to look inside, and we built this kind of Apple store next door. Here we store xenon. This is our data acquisition system. This is the cryogenic system to liquefy the xenon, to cool it, to keep it cool, to purify it constantly. Inside the water shield, it looks like that. Everything is cladded with highly reflective foil to tag the muons that we have there. And inside here, there is the volume with xenon. Xenon is cold. Everything here is at normal temperature. So this is a double wall cryostat, like your coffee cup, to insulate it thermally from the environment. So now I show you a small video. If you dive into this water shield that is usually not illuminated, you see This is really the cryostat with our detector. We sit here on a little cart that is used to bring radioactive calibration sources close to the detector. And now we move up again on the other side, just to give you an impression how this detector looks like. So it's basically a gigantic shield just filled with water. The detector itself is inside that cryostat, and this is a few impressions from how you build such a detector. Everything happens in a clean room environment, because you want to avoid dust and things like that. Here's a picture of the photosensors, and now the time projection chamber itself is moved under the detector. Everything was wrapped because we assembled the detector above ground. Now it was brought underground. This is now already in the center of the water shield, where we build another clean room, and then we lift everything up and put it here in the center of this water shield. Of course, all this structure, the clean room here, gets removed afterwards. And this was the largest xenon time projection chamber ever operated, about 1 meter in size, in diameter and height. And the active xenon target inside, searching for dark matter, was 2 tons. So in the last part, I will now show you a few results. I'm running a bit late, I have a feeling, so I have to skip something. I will see.
No, you're fine, Mark. You're absolutely
okay.
fine.
Okay, so you tell me if it's getting too long. I will show you a few selected results, what we've done with this detector. But first, what is the general search strategy? And it's essentially the same for every rare event search. What you want to do is you really want to find the needle in the haystack. So the most important thing is reduce your background. Get rid of as much as hay as you can. The other thing is you need to know what you're looking for. You need to know the shape and the color of the needle. Otherwise, you will never be able to find it. But you also need to know what are the backgrounds. So what can mimic a signal that looks like a needle? And both of them requires a lot of detector calibration. You really need to understand your detector extremely well. You need signal and background. How are they distributed in your detector? How do they look like? And then there's a very important point. Perform a blind search to avoid bias. So that means the region of interest, the parameter space where you aim or where you want to see your signal, don't look at it during analysis, because otherwise you will either find it or will not find it, depending on whether you wanted to find it or not. This human bias is well understood. So what we do is we really blind that region. Our PhD students, our postdocs are not able to see the relevant data. And only if the entire analysis chain is ready, we unblind and we check whether what we see is just the backgrounds that are well understood, or whether we see an excess that can then be attributed to a signal. And this comparison of do we see something above the known backgrounds would not work properly if we don't do a blind search. So how is that done for dark matter? We calibrate. So what we have here is just the light signal and the charge signal, and each event consists of a light and a charge signal. So each event is just a black point here. Now we use a calibration source that is representative for the background. We use a calibration source that is representative for the signal. And you see the red lines here correspond to the red lines here. The blue corresponds to the blue here. You see the separation in two distributions. So that's the most important thing. The second thing is you check how your real background, so not the background that corresponds to a calibration, comes from a calibration source, but the real background from radioactivity, from muons, is distributed in your detector. And this is shown here. This is just the radius. So basically what is shown here is the cylindrical detector. It's radius versus depth. This is shown here, radius versus depth. And you see that most of the background sits at the edge of the detector, either on the top, under the bottom, or at the wall. So for the search itself, you just take that inner part here, which gets rid of many, many backgrounds. Now you look at the real data. So basically that data that you see here corresponds to that data here. This is the background. This we are allowed to see, but in that region, we would expect dark matter, and that region is blinded. So we don't look at it during the analysis. And once we, the important point here is we are the largest dark matter experiment operated so far, and larger detectors make it easier to reduce the background. So the background that you see here was accumulated over almost 1 year of data taking with a 2-ton detector. It's the lowest background ever achieved by these kind of experiments. So just a few events here. And when you unblind, this is now a very complicated plot. For the sake of time, don't go into details. There's a WIMP search region here. It's basically a WIMP search region in many parameter spaces. That makes it complicated to show. There's no excess. So whatever we see is compatible with our expectations. One example could be, for example, this event. You say, well, it's right smack on in your region of interest. Why is that not a dark matter particle? Well, because it is extremely close to the bottom of the detector. So for each of these events, you can see that there's something fishy. So if you find nothing, what do you do with that? We are very, very good in finding nothing. We do that since many years. So what do you do with such a result? This is our parameter space. This is the unknown WIMP mass. This is the unknown coupling strength, and we do not even know the interaction. So we have to pick some model for the interaction, but of course there are others here. And well-motivated physics models live somewhere in that parameter space. For example, these generic dark matter WIMPs would live down here. And from the sheer fact that we observed with a certain detector size for a certain amount of time, we didn't see anything, we can exclude certain interaction strength, because otherwise we would have seen a signal. And this is what we do here. We produce exclusion plots. So basically everything that is green here, everything above here is already excluded. Our result is the line down here, and everything above is excluded, and all the others are other experiments. Since the WIMP mass is not known, you do that for every WIMP mass. You do that exercise. If a WIMP of that certain mass exists, then this corresponds to a certain flux of dark matter particles in our detector. We haven't seen them. We can exclude that. That's all. We can exclude that with many searches, and we did that very successfully. So our detector Xenon 1-ton produces the best dark matter limits above 110 MeV. So that's a tenth of proton mass up to basically many thousand proton masses. That's the black lines here. I think I will skip that one here. And I will show you the search that triggered your committee to ask our collaboration to give such a talk, is this electronic recoil search. So you've just seen that plot here, and I told you in our dark matter search, these numbers of particles are really, really small. And here we treated it as background. It's the lowest dark matter background ever achieved so far. And this background is from electronic recoils, mainly beta particles. It's basically daughters from radon decays. We know that very well. The question is, maybe that's something else here. There are dark matter models or other new physics models that predict something here. Since this is the lowest background ever achieved, well, let's look. Well, what you do, you define your region of interest. You need to know your backgrounds. I will not go through the list. It's a total of 10 components. And now the search is kind of easier. It's really just energy versus events here. So it's a one-dimensional analysis. The region of interest, we also don't know what to search for. We just say, okay, low energetic electronic recoils. And if we fit this model, the 10 backgrounds, to our data, you see it's a perfect match. And again, of course, it's the world record background level. So that's the exciting part. We seem to understand everything. The exciting part is down here at lowest energies. At lowest energies, it does not fit. And of course, if you do that initially, you just say, well, it does not fit. Let's refine the analysis. But we did that for 1 year and it does not go away. So we really have this small excess at lowest energy before it goes down again. It's about 50 events more than we expect. And if you know statistics a little bit, it corresponds to a 3.3 sigma fluctuation. If you don't know what that means, it is not relevant. It's something at the limit of being statistically significant. If that number would be considerably smaller, everybody would just say, okay, it's a statistical fluctuation. It would be much larger. Everybody would say, oh, wow, that's really something. So we're really somewhere in the ballpark where it starts to get interesting. The question is, what is it? And now I will very quickly come back to the axions. Axions are, like dark matter WIMPs, hypothetical particles. We haven't found them. They were invented not to solve the dark matter problem, but they were invented to solve a theoretical problem in particles physics, the so-called strong CP problem. Does not matter for that context here. The nice side effect is they solve the strong CP problem, or they would solve that strong CP problem. We haven't found them yet, but they are also excellent dark matter candidates. They are much, much lighter than WIMPs, have a different production process, and couple very, very weakly to photons. That is the difference. And they would interact with electrons. And if axions exists, because they are so much lighter than WIMPs, we, with our detector, have no chance to see the real dark matter axions. But if they exist, they are a new particle. They could be created. And in the sun, the sun is hot. We can calculate the temperature of the sun in the center. This corresponds to kV energies, and these photons of kV energies could convert into axions in the magnetic field of the sun. So we would expect that our sun is a constant source of axions of somewhat higher energies, 3-ish kV. And these so-called solar axions, they don't solve the dark matter problem, but we could detect them. And if we can detect solar axions, there's a very strong hint that dark matter axions also exist. The third idea is axion-like particles. That, well, I like this kind of particle hypothesis of an axion, but if I don't solve the strong CP problem, I just have a particle that is less motivated, but people think about it. And the thing is, we can detect it in our detector. In our detector, it would produce a signal like that. So this is now, again, the energy scale. And you remember our region of interest was from 0 to 30 or something like that. So that would produce a signal here from 0 to 10-ish kV. Other things that we considered was this axion-like particle as a dark matter candidate that would produce a line somewhere, but since we don't know the mass, we don't know where the line is. And the other thing we checked is a property of a neutrino. And the nice thing is, or the sad thing is, all these models fit our access. So basically, whenever we fit solar axions, neutrinos, or these bosonic dark matter axion-like particles, they all can describe these additional 50 events. The spectrum, the spectral feature is just not pronounced enough. We published that result in June, and since then we have almost 185 publications, citations. There are many, many other models made public by colleagues that equally well describe that. So the thing is, what have we found? We have found an excess that could be compatible with many signals of new physics. And now comes the big but. It is also compatible to a new background. If we have a tiny amount of tritium in our detector, you know, tritium is the heavy sibling of hydrogen. Hydrogen is just a proton and an electron. Tritium is a proton, 2 neutrons, and an electron, and it's radioactive, and it decays with such a spectrum. If you have a tiny amount of tritium in our detector, we can also describe the excess. And while, of course, all these kind of things here, this is Nobel Prize physics, this is just a mundane background. The problem is, we know how tritium could get into our detector. Everything that we can't quantify tells us it's probably not tritium. But at this point, we cannot exclude it. And with the limited data that we have, we cannot use the slightly different spectral change to distinguish. There was a question. Does it make sense to answer it here? Otherwise, let me quickly finish that part. before I'm almost ready to close. So this is the excess summary, the summary of this excess that we recently published. We see an excess, an unexpected excess of events above our known backgrounds. There are many, many, many models that describe it. There are some that we could exclude. It might be an unknown background. At the moment, we simply don't know. Okay, let's go to that question, please.
Happy just to sort of run through to the end, Mark, or
okay. If the question is not to that, then we go back to the end. Okay. So what do you do if you have such a problem that you have to solve? Well, we always do the same. We build bigger detectors. We wanted to build that detector anyway to have a higher sensitivity to dark matter, but this detector that we call Xenon N-ton is about 3 times as big as the old one. It has a 10 times lower background. And will be able to distinguish the axion hypothesis from the tritium hypothesis with about 1 year of data. You see that detector exists, and we are currently commissioning it in Italy. We build it, all our detector, the main physics channel that we're looking at is really to search for dark matter. All the other things is just a nice side effect. And the sensitivity on that plot is more than an order of magnitude better than what we've achieved so far. So you always want to go down lower here. There's another experiment that's called LZ, or Lux Zeppelin, which is important to mention to you because the Zeppelin part is actually colleagues from the UK that participate in that experiment. That is essentially identical is the wrong word, but it follows the same principles as our detector, and it is currently under commissioning in South Dakota in the US. And these are the sensitivity is essentially identical. Now you might ask, how do you continue? You build a bigger detector, you go down, you build another bigger detector, and you go down. But if you recall the beginning of my talk, well, there is some limit, and the limit is the sun. The sun produces neutrinos, and these neutrinos at some point will produce signals that look like dark matter signals in our detector. And this is dubbed as this neutrino floor that you can see here. It's not a hard wall. It really considers like some fog or so. So there is a way to get a little bit into that floor, but at the end, you cannot get very far, simply because the background signals that look like your signal are basically a number out your signal. And you see it's basically only 1 order of magnitude below what we want to reach with this next generation of experiments. And what we are currently already preparing is really this next generation detector that we call Darwin, dark matter Wim search with liquid xenon. It aims for an exposure, this is target mass times exposure time, of 200 tons years, which is about 200 times more than what we have done so far. And this detector would be still, let's say, not small, but compared to the gigantic experiments in astronomy, satellites, or also the detectors at the Large Hadron Collider in Geneva is still heavy. It's 2.6 meters. We aim for a total 50 tons of dark matter target inside the detector. And of course, with such a detector, you can do many other things as well. In neutrino physics, you can probe this signal excess that I've just mentioned to you. There are many, many challenges, and the scale of such a detector could then be like that. You need a larger water shield. But building the detector itself is a real challenge because it is not sufficient to just make the detector bigger. Every step you make it bigger, you also have to reduce the radioactivity. But I told you everything is radioactive, and you have to build a detector out of something. So that means you really have to see, how can I make walls thinner? How can I use different materials? How can I invent different methods to make my detector as little radioactive as possible? And there's one thing that I'm doing within my group to give you a feeling how big these detectors are. So this is basically a tiny, just a 5 centimeter high part filled with liquid xenon, but at the full Darwin scale diameter that we're currently building up in my lab to test horizontal components at the real scale. But now I really want to come to the end, so I hope I could show you a little bit that dark matter is a very interesting topic to look into, simply because it's 6 times more abundant than ordinary matter in the universe and had a crucial impact on the structure formation in our universe. And within the Xenon and Darwin collaborations, we have operated the most sensitive detectors already. We are currently commissioning the hopefully then still to be most sensitive detector Xenon Anton, and we are still planning for the far future. So if you decided to fall asleep during the talk and you just want to get the take-home message, these are the real simple take-home messages. 95% of our universe is dark, and we currently don't know what it is. 27% of the universe is dark matter. Dark matter means it's really dark. It neither absorbs nor emits light. So this is different to a gigantic black hole. A gigantic black hole would absorb light. Dark matter doesn't even absorb light. You can just look through it. We have no clue what dark matter is. We search for dark matter by playing pool billiard, really looking for particle interactions with the nucleus, and this nuclear motion then creates our detector signal. We use liquid xenon detectors for that because they are ideally suited for such a search because of their low background. Unfortunately, or well, that's a fate, we did not find dark matter yet, but we made other very interesting observations. Thank you for your attention.
Oh, brilliant. Thank you very much, Mark. Let me just unmute everybody for the moment, and I'd just like to invite everybody to show our appreciation to Mark in our own way. What an absolutely fascinating talk, and you know, a talk about sort of nothing, if you like, in terms of dark matter.
I can tell you, we get a lot of money for finding that.
But I think absolutely fascinating in terms of the struggle that you and the team and your collaborators are actually going through in building ever sort of more, you know, more sensitive detectors and different techniques, and sort of, you know, bigger isn't always better, and the issues you've got with radioactivity, intrinsic radioactivity, and so on. And I loved your metaphor about the finding a needle in a haystack, and then you started to introduce tritium and so on. It's like you're adding new hay to the haystack rather than removing it.
That's really the thing. Basically, with every generation of detectors, you find new backgrounds become relevant. The less sensitive detectors, you can ignore them because they are outnumbered by other backgrounds. But then you tackle these backgrounds, reduce them, and then suddenly another one becomes relevant.
Yeah, absolutely, absolutely. We've got some additional questions that have come in, Mark. If you have some time to answer them.
Yeah, of course. I just don't see them when I share my screen.
No, that's fine. I mean, feel free if unless you want to refer back to slides.
That depends on the questions.
Yeah, indeed. So we have one from Peter. How do you decide how long to run an experiment?
That's a very interesting question, and at the end it also boils down to the question of your background level and knowing your background level. Ideally, you want to search for every rare event in a background free condition. So basically, imagine you know that for a certain amount of time you take data and you expect zero background. Well, zero means in our case always 0.0001 or something like that. Then you only see one event, and in principle, that's a detection. That's the thing. If you expect 4 events, and you find 6, nobody will be excited because that is not a detection of 2, but this is just an upward fluctuation of the background expectation. So basically, we decide how long to run based on the background level. How long are we essentially background free? Because when you start to get into the background dominated regime, you're basically not acquiring sensitivity as efficient as in the background free regime. That's why for us it makes much more sense to build a new and better detector with a lower background rather than continue running an older instrument for 10 years or so. Because with just 1 year with a new instrument, you can basically do the same than with the old one in 10 years.
Great. Thanks, Mark. You mentioned at the start imagining dark matter as a halo around galaxies. Do you expect to see it exist as a smooth field or as lumpy as in a halo? And what about in intergalactic space? How might you perceive dark matter sort of permeating through?
Yeah, it's kind of a tricky question, because most of the answers here really come from this large, we call it N-body simulations that I have shown a little bit. Because we cannot really see it, what we do is we try to run the simulations of the universe, of fractions of the universe, but some groups are also doing that now with galaxies or clusters of galaxies. And the trick is, what you do is you basically put in some starting conditions that are usually motivated by this cosmic microwave background. And then you put in some physics, and then you just let the thing evolve. Everything is governed by gravity. And then you look at the outcome. And in this simulation, you can see the dark matter. Now, the trick is, the best simulations nowadays, they simulate dark matter, but they also simulate the visible matter. And the idea is then to really check the outcome of the simulations and compare whether the distribution of the visible matter corresponds with what you observe for the visible matter. Simply because there's so much more dark matter than visible matter, the visible matter will follow the dark matter. It behaves slightly differently because it has more feedback because of different interactions, but it generally follows the dark matter. And from these simulations, we don't expect a lot of structure inside our dark matter halo itself. So we don't really expect these gigantic voids in between filaments of galaxies and galaxy clusters that we expect for the largest scales, but it is totally not excluded. So about 8 years ago, there was a publication by some authors that basically looked at this question, how much dark matter is here at the position of the sun in the galaxy, and they said it's 0. They did one of these measurements of the local density, and people thought about it seriously. Is that possible? By now, the value is up again at this 0.3 protons, but it's not excluded that it would be the case. So it is not expected that it's non-smooth, at least at a rather coarse level, but you never know.
Okay, great. Is there any relationship? I think you sort of answered it in part with your answer just a moment ago. But the next question is there any relationship between the cosmic filaments that you described, that cosmic web, and dark matter?
Yes, the cosmic web is there because of dark matter. If dark matter would have different properties, if dark matter would not be cold, but moving at relativistic velocities, the cosmic web would look differently. Much more diffuse and with less contrast.
Great, thank you. That was from Clive. From Steve, we've got, is it justified to assume that the galaxy's dark matter halo does not rotate? And you mentioned
yes.
And dynamical friction.
Maybe you know how. So of course the halo is not standing still. Maybe you know how globular clusters move in the galaxy. They also don't follow the galactic rotation, but they have this trajectories. Basically, they go through the galactic plane, then try to escape the potential well of the galaxy, but then, of course, get back because they're trapped in the galaxy and go back. And these kind of chaotic trajectories through the galactic plane you have to expect for the dark matter halo. That means if you look at the average of the thing, of course, it's a maximum Boltzmann velocity distribution, but the average is at 0. And that means if you now have the moving sun through that galactic halo, you get this 230 kilometers per second as, let's say, the important number of that problem. Of course, there are dark matter particles that approach us, and there are others that come from the back. But this is the next order of complication.
Excellent, thank you. And a final question in the chat from George, and it relates to using materials that are radiation free. He's saying, am I correct in thinking that the steel you used to build the detector comes from battleships which were sunk before the start of the nuclear age?
No.
No.
So I guess you've heard about.
Great question.
It is a great question. And it's very well motivated. So the point is, this is indeed done for lead. So our experiment does not use lead, so we don't need it. But there are competing experiments, different technologies that need lead, and they really use so-called ancient lead that was used by the Roman as a counterweight at the bottom of their battleships. It was below the sea level, shielded from cosmic rays. That means shielded from cosmic activation. It's now also stored underground, and this has particularly very low radioactivity levels. For steel, that does not really make sense because the dominating radioactive isotopes, the relevant ones for us, are from the uranium and thorium chain. They are produced, they have half-lives longer than the age of the universe. They are produced in supernova, they're everywhere. So basically, this nuclear age that really started 50 years ago is irrelevant for us. Some of our competitors had sometimes problems for example, due to the Fukushima fallout. Japanese colleagues, they saw some contamination of aluminum, an aluminum isotope in some aluminum seals they used also. So this is a danger, but at least for stainless steel, this is not the case.
Great. Brilliant. Thank you, Mark. That's the end of all the questions that have come in via chat, and we didn't get any via our YouTube friends that joined us. So unless there's any others that anybody wants to, and I will unmute everybody. Or you have the capability to unmute yourself if you wish to ask a question. I'll give you just a few seconds. No. Gone. Okay. So I think, Mark, I mean, what an absolutely sort of cracking topic to get us off to a fantastic start for 2021 in this brave new world to looking for dark matter, and you know, fingers crossed that you'll be successful in that endeavor over the coming months or potentially years,
well,
I guess.
Coming years is the proper time scale.
Yeah. Excellent. Well, you know, I think hopefully we've got a hotline through to your office now, in case you want to come to us first to make any major announcements. We'd be more than happy to act as your agent in the UK on this. But for now, I think if we can just sort of once again thank Mark for a absolutely fascinating talk, and you know, wish you a happy new year to you and your team, and good luck and good hunting.
Yeah, thank you. Thanks for the invitation. Thanks for the interest.
Brilliant. So Mark, what we're going to do now is just, you know, keep the line open, and if you know, feel free to stay or to log off as you wish. But we just wanted to sort of keep our conversation going with those on the line, and any other sort of general queries and so on. But
so if you don't have other questions to me, I think I will log off.
Brilliant, great. Thanks very
Good
much.
night.
Good night.
Bye-bye.
Bye. Bye.